Generating the light that prints modern microchips demands the violent precision of instantly vaporizing a microscopic liquid target. ASML held a strict monopoly on this exact process for 20 years, but China has now successfully constructed its own domestic prototype. This chart outlines China's current roadblock. To produce advanced chips, they rely on an older technique called quadruple patterning DUV. They force the same silicon wafer through the machine 4 separate times, destroying their chip yields in the process. To escape this dead end, China has unveiled a domestic extreme ultraviolet, or EUV, prototype that completely abandons conventional design logic. A standard ASML scanner is roughly the size of a school bus. China's new prototype reportedly occupies an entire factory floor. So why is China's new machine so massive? The answer reveals the strict physical boundaries of reverse engineering and what happens when you attempt to build an entirely domestic system without access to its most critical parts. ASML's industry-standard approach is known as laser-produced plasma. It requires hitting 50,000 flying tin droplets every single second without missing a single shot. Lacking the decades of development required to achieve that targeting precision, China revived an alternative method, Laser-Induced Discharge Plasma, or LDP. Rather than chasing flying targets, the LDP system relies on 2 thick metal discs slowly rotating in liquid tin. A small laser fires at one disc, vaporizing tin to create a hovering cloud between the wheels. Then, massive capacitor banks dump their energy, sending a violent electrical arc straight through the vapor, crushing it into a brightly glowing sphere of extreme ultraviolet light. ASML actually tested this exact discharge method 20 years ago, but abandoned it. They found that as engineers pumped more energy into the system, the plasma simply grew larger, but not brighter. China's strategy assumes that 2026 is not 2006, betting that 2 decades of material science can finally brute force an old technology into a viable tool. Generating the light is only the first step. At 13.5 nanometers, extreme ultraviolet light behaves differently. Standard glass lenses absorb it entirely instead of bending it. To direct the beam, these machines must use mirrors built from dozens of atomically thin, perfectly alternating layers of molybdenum and silicon. This animated chain illustrates the problem. Every single reflection absorbs at least 30% of the light. By the time the beam navigates the entire labyrinth, only a tiny sliver reaches the wafer, leaving zero margin for error. Achieving the required atomic smoothness took the German optics company Zeiss over 30 years to perfect. China does not have 30 years to catch up. When you cannot manufacture optical components with picometer precision, you have to compensate physically. You build larger collectors, lengthen the optical path, and use massive mirrors to capture the scattered light. This specific physical compensation is exactly why the prototype occupies an entire factory floor. The sheer monolithic footprint of the machine is the direct consequence of missing optical precision. Without the ability to engineer microscopic perfection, the only remaining option is monolithic scale. But there is one absolute bottleneck in semiconductor manufacturing that no amount of engineering scale can bypass: helium. This single element is required to perform 3 unsubstitutable tasks simultaneously. It carries away extreme heat, it protects delicate optics because it won't react with them, and its atomic structure is so small it can detect microscopic system leaks. An advanced fab drinks massive quantities of it, requiring up to 20,000 cubic meters every single month to keep production running. This chart exposes a severe supply chain vulnerability. While China's domestic helium production sits under 900 tons, it imports over 4,900 tons, with the vast majority historically flowing from the United States and Qatar. And unlike oil, helium cannot be easily hoarded in strategic reserves. It is shipped as a cryogenic liquid that slowly boils away if delayed in transit, meaning it must be used almost immediately. Beyond natural resources, bridging the development gap required specific lived experience. To accelerate their timeline, China heavily recruited returning overseas talent, specifically engineers who spent years developing ASML's original light sources. This machine's long-term survival rests on a fragile global supply chain of rare gas and imported human knowledge that sanctions cannot block. Looking at the raw performance metrics, The Chinese prototype currently peaks around 100 watts of output power, while ASML's production models easily generate 300 to over 700 watts. In a commercial setting, that lower power is a brutal handicap. It means the light is dimmer, the exposure takes longer, and the entire manufacturing process is vastly less efficient. Strategic sovereignty takes precedence over commercial efficiency in this domestic roadmap. The benchmark for this prototype is not ASML's latest model. It simply has to cross the threshold of being better than the failing quadruple patterning DUV process that is currently destroying China's semiconductor yields. The project prioritizes geopolitical independence, aiming to build a production line that foreign powers can never turn off. The next challenge is transforming this isolated prototype into a machine that runs relentlessly, 24 hours a day.